What if the universe is lying to us? What if the ultimate speed limit of reality is not a wall, but a challenge? Our galaxy is more than 100,000 light-years across a distance so vast that the human mind simply fails to grasp it. Even the very first radio signals humanity ever sent into space, traveling at the maximum speed allowed by nature, have reached only a millionth of the stars in the Milky Way. Light itself is the cosmic speed limit, and compared to the scale of the galaxy, it is painfully slow. So slow that any serious dream of interstellar travel begins to feel almost cruel, at least within a human lifetime. And yet, humans have always asked the same forbidden question. Is there a way around this? Is there a loophole in the universe? Can we go faster than light? Since childhood, many of us have looked up at the stars and imagined reaching them one day, crossing the cosmic ocean, exploring alien worlds, discovering life in all its strange and beautiful forms. But the universe seems to mock us. It allows us to see its wonders and then locks us in place, as if we are prisoners staring through the bars of a cosmic cell, free to dream but forbidden to go. It's no surprise that human ingenuity rebels against this limit. We have never been good at doing what the universe tells us we cannot do. Right now, we have no way to build a faster-than-light highway, not to Andromeda, not even close. We don't just lack the technology, we can barely imagine such a road. But physics leaves us clues, and scientists cling to them with quiet desperation. One of the most important is this: the speed of light is a limit for motion through space. Space itself is not bound by that rule. In fact, parts of the universe are already moving away from us faster than light, not because they are breaking the laws of physics, but because space itself is expanding. The fabric of reality is stretching in all directions. And from this, a dangerous idea emerges. What if we don't move through space? What if we move space itself? What if one day we learn to control the geometry of the universe? This is where one of the strangest ideas in modern physics appears: the Alcubierre drive. Inspired by science fiction, physicist Miguel Alcubierre discovered something shocking. Einstein's equations allow a solution, at least on paper, that permits faster than light travel. Not by breaking the speed limit, but by bending space around a ship. Space expands behind it and contracts in front of it, allowing a bubble of warped space to travel between stars at any speed. It sounds unbelievable, and it almost is. The problems are extreme. It requires exotic matter with negative energy. It demands absurd, almost cosmic amounts of power. It could flood its destination with lethal radiation. Optimists argue these are not fundamental obstacles, only engineering nightmares. But there is a deeper problem, one that does not care about optimism: quantum effects. In 2009, physicist Stefano Finazzi demonstrated something deeply unsettling. Inside a warp drive bubble, Hawking radiation doesn't simply appear, it accumulates, and it grows exponentially. This radiation would not only be lethal for the crew, it would eventually destroy the bubble itself. The drive collapses under its own quantum effects, and this problem is not unique to warp drives. There is another famous faster-than-light concept: wormholes. Hypothetical tunnels through spacetime, shortcuts between distant regions of the universe, but they suffer from the same disease: instability, quantum fluctuations, collapse. Every proposed superluminal system seems to be haunted by quantum physics. In the end, we cannot definitively prove whether wormholes or Alcubierre drives are possible, not until we solve the problem of quantum gravity, or until we build a working prototype. And beyond these ideas, there are many others: tachyons, quantum tunneling, entanglement-based schemes. Each comes with countless variations. Even the Alcubierre drive itself has been modified again and again in attempts to reduce its impossible energy demands. And physicists will certainly keep inventing new versions. So it would be foolish to completely rule out faster than light travel. On one hand, this is encouraging. It means hope is still alive. The dream remains. On the other hand, it is deeply frustrating. This is science. We don't want eternal maybes. We want answers. So can we say anything definitive with the knowledge we have? Surprisingly, yes. Even without a theory of quantum gravity, even with endless variations of faster-than-light ideas, there is one statement that applies to all superluminal systems, without exception. They all allow time travel, and that is where reality begins to break. Imagine you have a time machine. You decide to travel 70 years into the past to visit your grandfather. He is standing on a mountain near a cliff, admiring the view. You were never particularly fond of him. You push him. Gravity does the rest. Seconds later, your grandfather is gone. Stop. You just killed your grandfather before he ever met your grandmother. That means your parents were never born, which means you were never born. But if you were never born, how did you travel back in time to kill him? You don't exist yet. You committed the act. But if you don't exist, you couldn't have killed him. And if you didn't kill him, he's alive, which means you are alive, which means you can go back and kill him. An endless logical loop. This is the famous grandfather paradox. Physicists hate it because it attacks the logical foundations of reality itself. There is no clean solution, only a disturbing conclusion. The paradox is not a paradox at all because the situation it describes is physically impossible. You cannot kill your grandfather. Not because of morality, not because of fate, but because the universe forbids it. To understand why, we first have to answer a deeper question. Why are physicists even forced to take time travel seriously in the first place? Let's start with something real, not wormholes, not warp bubbles, something you can test with a clock. Imagine you have a brother. You synchronize your watches and he flies into space on a shuttle moving at about 28,000 kilometers per hour. He circles the Earth and comes back. His watch will be behind yours, not by much tiny fractions of a second, but it will be behind. That effect is called time dilation. Time measured along different paths through space-time changes, depending on speed and gravity, and each affects time in its own way. Einstein's relativity doesn't treat time as a universal river flowing at the same rate everywhere. Time is local. Time is conditional. The faster you move, the slower your clock ticks relative to someone at rest. The deeper you are in gravity, the slower time runs relative to someone higher up. The easiest real-world example is the International Space Station. Astronauts on the ISS age slightly less than we do on Earth, on the order of hundredths of a second per year. It's a small difference, but it's measurable. And the moment you push speeds closer to the speed of light, the story stops being small. Up to around 70% of light speed, relativity still feels tame. But once you pass roughly 3/4, things start to get dramatic. Not just time, but space itself. Here's where reality gets weird. Distances contract in the direction of motion. Suppose you travel to Alpha Centauri, about 4 light-years away, at 90% of the speed of light. From Earth's perspective, a round trip sounds like roughly 10 years. But inside the ship, your own clock doesn't agree. Time slows for you, and the distance you're crossing shrinks. So for the crew, the trip can feel like just a little over 4 years. You return not with stories of alien planets, but with a more terrifying souvenir. You're now years younger than everyone you left behind. That is real time travel. Not to the past, but to the future. And to make this even more concrete, there's a famous example many people already know: Interstellar. The team lands on a shallow water world near the black hole Gargantua. The planet is in an extreme environment, intense gravity, extreme orbital speed, and a black hole with a mass on the order of 100 million suns, rotating at nearly the speed of light. Put all of that together, and time near the planet crawls compared to time far away. In the movie, 1 hour on the surface equals 7 years for their friend waiting in orbit. They spend a little over 3 hours down there, and when they return, he has aged 23 years. The most unsettling part is this: it isn't fantasy physics. The numbers were designed to be consistent with general relativity, and the calculations were overseen by Nobel laureate Kip Thorne. In principle, this is exactly what extreme gravity can do. The crew didn't skip time by magic. They rode the geometry of space-time into the future. So time travel to the future is not the mystery. It's already built into the laws of nature. The real nightmare is time travel to the past. To even talk about that, physics introduces something with a dangerous name: a closed, timelike curve, a loop in spacetime that, in theory, allows an object to return to its own past. To visualize it, don't imagine time as an arrow moving from yesterday to tomorrow. Imagine spacetime curved so severely that forward eventually bends back onto itself like a ring. You keep moving forward second by second, step by step, but at some point you arrive at the very event you started from. Same place, same time. You could meet yourself right before departure. This possibility was first uncovered by Gödel, one of the greatest logicians who ever lived and a friend of Einstein. Gödel found a solution to Einstein's equations describing a rotating universe where closed, time-like curves can exist. In such a world, if you move in the right way around the cosmic rotation, you can at least mathematically return to yesterday. Einstein was disturbed. The math worked, but common sense screamed. Let's return to the grandfather at the edge of the cliff. Remember, we said there is a solution that makes the murder impossible. If closed time-like curves exist, physics invokes something called Novikov's self-consistency principle, and it states something radical. The probability of any event that creates a paradox is zero. The universe does not tolerate contradictions. In this view, the past is immutable, not because time travel is forbidden, but because it has already happened. If you travel 70 years into the past, you are not entering an editable draft of history. You are stepping into a chapter that already includes you. Every action you take there is not a change to history, but part of the only history that exists. You approach your grandfather, you intend to push him, and something always intervenes. You slip on a stone at the last moment. You collapse from a heart attack. The gun jams. The bullet disintegrates. Twists just enough to stop the contradiction. You cannot kill your grandfather because you did not kill your grandfather. History is won. The loop is closed. Any attempt to change the past becomes the very mechanism that produces the future you came from. In this scenario, physics turns into a ruthless scriptwriter. Free will becomes an illusion for the time traveler. You may want to pull the trigger, but the laws of nature will conspire against you. The universe will bend, break, and contort itself if necessary, but it will preserve its logical integrity at all costs. It sounds almost schizophrenic, and yet, mathematically, it is perfectly consistent. What's unsettling is that physics does not actually forbid time travel outright. There are legitimate solutions to Einstein's equations in which returning to your own past is possible. The mathematics works cleanly, elegantly, and still, we don't see visitors from the future. No tourists, no warnings, no proof. So why? Perhaps nature hides a protective mechanism where we least expect it. Perhaps the real prohibition against time travel is not written in gravity or quantum mechanics alone, but in something far more intimate. In memory, in causality, in the irreversible buildup of information, in the arrow of time itself, the thing that makes experience possible and life meaningful. This video is largely inspired by Eternity, In Search of the Ultimate Theory of Time by theoretical physicist and cosmologist Sean Carroll. If this subject truly fascinates you, you'll get even more from reading the book than from watching this video. St. Augustine once admitted something strange and honest. If no one asks me what time is, I know. But if someone asks me, I cannot explain. Try a small experiment. The next time you're killing time in a bar, on a plane, or standing in line for some document, ask the people around you a simple question. What is time? You'll get many answers. Time moves us through life. Time separates the past from the future. It's what a clock shows. My personal favorite was, time is the clock frequency of reality. Everyone will be right, and everyone will be wrong, or rather, only partially right. That's the paradox. In everyday life, we handle time flawlessly. We check clocks, we plan trips, we show up late or on time. Time is incredibly useful to us, even though we can't give it a clean, complete definition. It's like Supreme Court Justice Potter Stewart trying to define hardcore pornography. He famously said, "I can't define it, but I know it when I see it." Time feels the same way, intimately familiar, conceptually slippery. So what do we actually mean when we talk about time? The universe doesn't hand us concepts ready-made. We observe phenomena, notice patterns, and invent definitions to describe them. Most of what we call fundamental is invented for convenience. But time feels different. It feels too basic, too deeply woven into reality, to be something we just made up. And yet, we did. Time has three different faces, and all three matter. First, time marks moments in the universe. It's a coordinate, a way of locating events. Second, time measures duration, the interval between events. That's what clocks are for. And third, time feels like a flow, a river, carrying us from the past into the future. At first glance, this all sounds like the same thing. But if you look closer, you realize these aspects are logically independent. They don't have to go together. They just happen to be tightly intertwined in our world. And that raises a deeper question. Why? Let's start with the first face of time. Time as a marker of moments. John Archibald Wheeler, the physicist who gave us the term black hole, once offered a deceptively simple definition. Time is what prevents everything from happening at once. It sounds almost trivial, but it cuts straight to the heart of the problem. We experience the world as a collection of things in different places. Physics bundles all those places into a single concept: space. Atoms, particles, fields, rooms, planets. All of it exists together as the world. You are in a room. Around you are furniture, books, people, air molecules. This entire configuration exists at once. But the world doesn't stay the same. It changes. Right now, the cat is sitting on your lap. In a minute, it will jump to the floor. You never see both states at the same time. First one, then the other. Time is what lets us distinguish between these configurations. It allows us to say, the cat is asking for food now, but a minute ago, it was sleeping in my arms. The world is like a film reel. Each frame is the complete state of the universe at a specific moment. Time is what arranges these frames in the correct order. Without time, reality would collapse into a meaningless jumble of images, something like avant-garde French cinema. There is one property reality never abandons: continuity. A cat can jump off your lap, but it doesn't suddenly vanish from existence. Change is smooth, predictable. Because of this continuity, we don't see the world as a collection of frozen snapshots. We see stories. A cat is not just a pile of cells, it is a being with a history, stretching from birth to death. Physicists give this history a precise name: a world line. It is the path an object traces through time. Now imagine you want to meet a friend. You don't just agree on when, you also agree on where. Location in space requires 3 numbers: coordinates, latitude, longitude, height. 3 numbers fix a point in space. Time adds a 4th. Any point in space at any moment in time is what physicists call an event. It doesn't have to be dramatic. A random point in an empty room right now is an event. The universe, then, is the totality of all events, every point in space at every moment in time. Pause for a second and let that sink in. Instead of a universe that constantly changes, we suddenly see something very different: a single 4-dimensional object. Space-time. Time doesn't move this object forward, it slices it, like a knife cutting bread. Each slice is the entire universe at one moment. An infinite stack of such slices is what we experience as reality unfolding. That was the first phase of time, ordering moments. The second phase is duration, the length between events. Time doesn't just tell us what comes after what, it tells us how much separates them. Take a YouTube video. It lasts an hour. When you finish watching it, the clock on your wrist also shows 1 hour has passed. But why should we trust that clock? What makes a clock accurate? The answer is surprisingly simple: regularity. A clock is anything that repeats the same process over and over again, uniformly. But uniform compared to what? Compared to other clocks. And here's the key empirical fact about the universe: there exist processes that repeat with astonishing stability. The Earth completes 1 orbit around the Sun in a year. Mercury does it in about 3 months. Uranus takes 84 years. This isn't coincidence, it's structure. The Earth rotates around its axis roughly 365 times per orbit. A quartz crystal in a wristwatch oscillates more than 2 billion times per day. And those oscillations are incredibly stable. Temperature changes, pressure changes, the rhythm survives. In 1581, a young Galileo was stuck in a long, boring church service. Above him, a chandelier was slowly swinging. Large swings seemed faster, small swings slower. The result shocked him. The period stayed the same, independent of amplitude. This is a fundamental property of pendulums, known today as simple harmonic motion. And that's why pendulums became the heart of clocks. Watchmaking, at its core, is the search for reliable repetition. From pendulums to quartz crystals to atomic and nuclear resonances. So when we say the video lasted an hour, what we really mean is this: the quartz crystal oscillated about 118 million times. Notice something important here. We define time without ever using the concept of time itself. That's not a flaw, that's necessity. You cannot define something using itself. Now for a deceptively tricky question. What if time slowed down everywhere in the universe? The answer is simpler than it sounds. The question is meaningless. Slowed down relative to what? If all clocks slow down together, nothing changes. No experiment can detect it. Humans feel time passing because of internal rhythms: heartbeat, breathing, neural firing. You are a complex network of biological clocks, but unlike quartz, your internal clocks are unreliable. They respond to emotion, stress, boredom. Sometimes time flies, sometimes it drags. Yet the molecular processes inside your body remain astonishingly regular. But now, imagine something more subtle. What if some clocks slow down relative to others? Normally, we'd blame the clocks. But if an entire class of clocks changes pace together, the question becomes unavoidable. Did the clocks change, or did time itself change for them? In Nicholson Baker's novel, The Fermata, the protagonist can stop time. The entire world freezes while he continues to move freely through it. It's a beautiful idea and completely impossible. If the air froze, he wouldn't be able to breathe or move. If light froze, he would be blind. In short, it's a poetic fantasy, but not physics. And yet, there's a real sense in which time can pass differently for different observers. Not because time stops, but because clocks can follow different paths through space-time. Time doesn't only put events in order. It also measures the distance between them. The year 1500 isn't just before the year 2000. It's exactly 5 centuries before it. Isaac Newton believed this distance was absolute. In his view, you could scatter clocks across the universe, synchronize them, and obtain a single universal time, one cosmic now. But in 1905, Einstein shattered that picture. Special relativity revealed something unsettling. The two aspects of time ordering and duration are not the same thing. If 2 clocks start at one event and reunite at another, but travel along different paths through space-time, they will show different times. This isn't a malfunction. It's not bad engineering. It's a feature of reality itself. Think of a football field. A player runs from the center to the opponent's goal. The change in position is 50 meters, but the path he takes might be 60 meters or 100, weaving between defenders. The displacement and the path are different things. Time works the same way. The time coordinate tells you where you are in space-time. The clock reading tells you how you got there. Time and space are deeply similar, but not identical. Space has 3 dimensions. Time has only 1. In space, the shortest path between 2 points is a straight line. In time, a straight path gives you the longest possible duration. And there is one difference that matters more than all the others. In space, you can move in any direction. In time, you move only one way from past to future. No one can turn around. No one can go back. Or can they? This brings us to the third phase of time. Time as a flow. We feel time rushing past us, or we imagine ourselves moving through time as if it were a river. Interestingly, the ancient Greeks imagined the opposite. The future approached from behind, unseen, while the past lay visible in front of them. It makes sense. We remember the past. We can only guess the future. But there's a problem with the idea that time flows. A river flows because water changes position. We can measure its speed, kilometers per hour. But what would be the speed of time? Hours per hour, 1 hour per hour. That's not a speed, it's a tautology. Time cannot flow relative to itself. The metaphor is seductive, but wrong. To think clearly about time, we have to abandon the idea that we are inside a current. Instead, try a more radical experiment. Imagine yourself outside the universe, not inside time, but looking at it from the outside. Of course, this is impossible. In reality, the universe is everything that exists. But as a thought experiment, it's powerful. Philosopher Hugh Price called this perspective the view from nowhere. A viewpoint not anchored to any particular moment. What would you see from there? Nothing would be changing. You would see all of history at once. Past, present, and future laid out together. In Slaughterhouse-Five, Kurt Vonnegut's Tralfamadorians perceive time exactly this way. They see every moment simultaneously, the way we see an entire mountain range at once. As Vonnegut writes, only we on Earth have the illusion that moments follow one another like beads on a string, that once a moment is gone, it's gone forever. If we look at the world through the eyes of the Tralfamadorians, what we see is not a flowing present, but a network of interconnected events arranged in a fixed structure. Here the clock reads 6:45 p.m. A person is holding a glass of water with an ice cube inside. Here at 6:46 p.m. the ice cube is floating. Here at 6:50 p.m. the ice is melted. The glass feels cool. Nothing moves. All of these moments simply exist. This picture is known as the block universe. Space and time together form a single 4-dimensional block of space-time. Time is not something that passes, it is something reconstructed from relationships between events. When we say the ice melted in 10 minutes, what we really mean is, when the ice was gone, the clock reading was 10 minutes larger than it was at the beginning. Not everyone accepts this view. Back in the 5th century, St. Augustine argued that only the present is real. The past exists as memory. The future exists as expectation. Everything, he claimed, exists only in the soul. This position is called presentism. The block universe view is called eternalism. Past, present, and future are equally real. Interestingly, physicists are mostly indifferent to this philosophical dispute. They care less about what is real and more about whether a theory works. What matters is structure, consistency, predictive power. The goal of physics is to build a single framework that accounts for all three phases of time: clock measurements, space-time coordinates, and our subjective experience of flow. The first two are explained remarkably well by Einstein's relativity. The third is not. And that's why understanding time requires stepping outside everyday intuition, learning to see the universe as a whole, and separating time itself from the way our minds experience it. This separation is not philosophical luxury. It is the key to understanding what time really is, and, ultimately, what time travel could even mean. To see why, imagine time running backward. You eat dinner, and the food jumps from your mouth back onto the plate. You take groceries home, then return them to the store and get paid. It sounds absurd, and that's exactly why reverse time is such a powerful artistic tool. In the curious case of Benjamin Button, Scott Fitzgerald gives us a man who is born old and grows younger with age. In Through the Looking Glass, the White Queen screams before she pricks her finger because she remembers the future, not the past. These stories disturb us because they violate something deep and familiar. In the real world, time has a direction. Time has an arrow. Play a movie backward, and you immediately know something is wrong. A diver jumps into a pool. Water splashes outward. That makes sense. But if waves spontaneously rise and push a person out of the pool onto the diving board, your brain rebels. Either the film is reversed, or something is very wrong with reality. Here lies a crucial asymmetry. In space, all directions are equivalent. There is no intrinsic up or down unless gravity defines it locally. Time is different. It always points one way. Why? Surprisingly, the arrow of time is not a fundamental law of physics. It is a consequence of our special situation in the universe. Just as Earth defines up and down in space, the Big Bang defines past and future in time. If you film a simple pendulum swinging, you cannot tell whether the video is playing forward or backward. The equations are symmetric. But film a diver hitting the water, and the direction is obvious. The difference has a name: the second law of thermodynamics, the most reliable law in all of physics. It states that the entropy of an isolated system never decreases. Arthur Eddington put it bluntly: if your theory contradicts the second law, it can do nothing but collapse in humiliation. This story begins in the 19th century with steam engines. The French engineer Sadi Carnot wanted to understand why British engines were more efficient than French ones. He discovered a fundamental limit. No engine can convert all its energy into useful work. Some energy is always lost as heat. Rudolf Clausius realized this wasn't just an engineering problem. It was a law of nature. Heat does not spontaneously flow from cold to hot. Drop a hot object into cold water, and temperatures equalize. The reverse never happens. To describe this irreversibility, Clausius introduced a new quantity: entropy, a measure of how much energy has become useless. Gasoline in a tank has low entropy. Its energy can do work. After combustion, the same energy still exists, but it has been scattered into heat, noise, and random motion. Entropy has increased. The real breakthrough came with Ludwig Boltzmann. He understood that entropy is not mystical, it is statistical. It measures disorder at the microscopic level. Take a glass of water. There are countless ways to rearrange its molecules without changing anything you can see. Now take an egg, mix the yolk and the white just slightly, and the change is obvious and irreversible. There are vastly more disordered states than ordered ones, and that imbalance is what gives time its arrow. Boltzmann captured it with ruthless clarity. Entropy measures how many microscopic arrangements of atoms produce the same macroscopic picture. Disorder has vastly more arrangements than order. And because nature doesn't prefer special arrangements, systems naturally drift toward chaos. That's why you can turn an egg into an omelet, but never an omelet back into an egg. You can mix milk into coffee, but you can't unmix it with a spoon. You can scatter papers across a table, but they will never gather themselves into a perfect stack. Entropy doesn't forbid order. It simply makes disorder overwhelmingly more likely. And paradoxically, entropy is what makes life on Earth possible. The sun sends us low entropy energy, concentrated, structured, usable. We consume that energy and radiate it back into space as high entropy heat. If the sun filled the entire sky, Earth would quickly heat up to its temperature, reach equilibrium, and freeze into boredom. Nothing would happen. No weather, no life, no history. Change exists only because entropy has somewhere to go. But here, we run into a deep mystery. If entropy is always increasing, then it must once have been extremely low. The universe must have begun in a state of astonishing order. Why? We don't know. This is one of the central unsolved problems of modern physics. What we do know is this: the arrow of time exists because we live at a very special moment in cosmic history, a moment when entropy is still far from its maximum, when there is still room for disorder to grow. This asymmetry doesn't just shape physics, it shapes memory itself. Imagine you see a broken egg on the sidewalk. From the pattern of the spill alone, you immediately know something about the past. A few minutes ago, the egg was whole, and then someone dropped it. The past feels constrained, almost obvious, but the future, completely open. The egg could dry out, be washed away by rain, eaten by a dog. It will not reassemble itself into a shell. That option is simply not on the table. A broken egg is a physical memory, a record of a past event. And such records can exist only because entropy was lower before than it is now. The same logic applies to memories in your brain. They are traces left by irreversible processes. If entropy were the same in all directions of time, memory itself would be impossible. Cause and effect follow the same pattern. We instinctively expect causes to come before effects. A diver jumps into a pool, a splash follows, never the reverse. In principle, the laws of physics allow water molecules to arrange themselves in just the right way to launch a diver back onto the board. But this would require an absurdly precise coordination of trillions upon trillions of atoms, possible in theory, impossible in practice. Philosophers call this intuition possibilism. The past exists and is fixed. The future does not yet exist and therefore can be changed. If your partner suggests changing your vacation plans for next year, you can agree and book new tickets. But if they suggest changing last year's vacation, you might start considering medical advice. The asymmetry is absolute in experience, even though the equations of physics make no such distinction. And this is where free will sneaks in. Our sense of choice exists only because entropy points one way. The future feels like a blank page. The past feels like a finished book. Now, let's return to the main question. What does all of this actually say about time travel? Remember, closed timelike curves, loops in space-time that, at least mathematically, allow a return to the past. On paper, they exist, but in reality, they collide with something far more brutal than paradoxes. The arrow of time. Imagine you manage to build a time machine. You press the button. You travel 70 years into the past, to your grandfather's era. Now ask a simple but devastating question. What happens to entropy? Your body is a low entropy system, highly ordered, structured, alive. You arrive in a past where the total entropy of the universe is lower than it was at the moment you departed. Suddenly, an object from a higher entropy future appears in a lower entropy past. That alone is a violation of the second law of thermodynamics. It gets worse. At the moment you left, the universe had a certain entropy value. At the moment you arrive, that value is lower. Does this mean entropy has decreased? That cannot happen in an isolated system. You might argue that the time machine is not isolated, that it exchanges energy with the environment. But the problem doesn't disappear. It only deepens. Your memories are oriented toward the future. You remember pressing the button. You remember the journey. Those memories were formed in a higher entropy state of the universe. Now, you find yourself embedded in a lower entropy era. How does your brain function there? According to physicist Sean Carroll, this is where time travel truly collapses. If you attempt to go backward in time, your memories don't survive the trip. Not because the machine malfunctions, but because memory itself is aligned with the entropy gradient. Your brain works by recording traces as entropy increases. That is your personal arrow of time. But if you enter a region where entropy is lower, your arrow conflicts with the arrow of the surrounding universe. What happens then? Perhaps your memories begin to dissolve. Perhaps they reverse. You forget the future and begin to remember things that have not yet happened, like the White Queen in Through the Looking Glass. Or perhaps something even worse occurs. You cease to be a conscious observer at all. Because consciousness is not timeless, it is a process. It depends on causality, memory, and anticipation, and none of those survive without a consistent arrow of time. This led Stephen Hawking to propose what he called the chronology protection hypothesis. The idea is simple. The laws of physics somehow prevent travel into the past. Nature protects causality, not morally, not philosophically, physically. The question is how. One possibility is quantum mechanics. We already saw how quantum effects sabotage warp drives. The same may happen near wormholes or any structure capable of forming a closed timelike curve. Quantum fluctuations could grow without bound, destroying the space-time geometry before time travel becomes possible. Hawking once joked that the best evidence against time travel is the complete absence of tourists from the future. And it's a fair point. If traveling to the past were possible, why has no one come back to tell us about it? Perhaps it requires a civilization so advanced that it has not yet emerged. Or perhaps any civilization that reaches this level immediately destroys itself through temporal paradoxes. There is another, stranger possibility. Maybe travelers from the future are already here. But Novikov's self-consistency principle forbids them from changing anything. Their presence is woven into history from the start. They don't alter the past. They are the past. In that case, history is not merely immutable. It is necessary. Every event is locked into every other, forming a single, self-consistent causal loop. So the arrow of time is not a philosophical metaphor. It is a physical barrier. Entropy is the jailer of time. It traps us in the present and forces us to move only one way forward into the future. But this raises a final, deeper question. What does it even mean to move in time? Einstein has become a cultural icon. His face is printed on t-shirts, his name is known to almost everyone, and his manuscripts sell for tens of millions at auction. And yet, very few people can clearly explain what he actually did. We imagine an absent-minded genius with wild hair, lost in abstractions. The real Einstein was different. That famous hairstyle appeared only late in life. The young Einstein looked neat, sharp, focused, and most importantly, relativity was not born from vague philosophical musings. It emerged from very practical problems. The special theory of relativity was not the work of one man alone. Several physicists were circling the same ideas, and mathematician Henri Poincaré made crucial contributions. Einstein's achievement was to bring everything together into a coherent theory. What drove this work was not metaphysics, but engineering. Einstein was working as a patent clerk in Bern, evaluating technical inventions. At the turn of the 20th century, one problem dominated modern society: accurate clocks. Europe was being covered by vast railway networks. Trains crossing borders required synchronized schedules. Timekeeping over long distances became an economic necessity. Poincaré, meanwhile, headed the French Bureau des Longitudes, where the problem was navigation. Maritime transport depended on precise determination of position on the open sea. The central questions of the era were not, where are we in the universe? Or what time is it in some absolute sense? But where are we relative to others? And what do our clocks show? Newton's ideas of absolute space and absolute time feel intuitive. Relativity demands something harder, abandoning intuition in favor of measurement. Physicists realized that the universe does not owe us comfort. What matters is what real instruments record. To see this, consider a thought experiment. Imagine yourself inside a sealed spaceship, drifting freely through space. You have food, air, and scientific instruments, but no windows. You cannot see outside. What can you learn? Acceleration is obvious. When the ship is not accelerating, objects float freely. When the engines fire, objects fall toward the floor, opposite to the direction of acceleration. Rotation is also detectable. Objects near the axis remain still, while objects near the walls are pressed outward. But some things remain forever hidden. You cannot tell where you are near a planet or deep in interstellar space. You cannot determine your speed. Once the engines shut off, the ship drifts uniformly at whatever velocity it has acquired. You cannot even define an absolute orientation, because in space, all directions are equivalent. These simple facts reveal something profound. Any change that does not affect the outcome of experiments corresponds to a symmetry of nature. Shifting your position is called a translation. Changing orientation is a rotation. Changing velocity is a boost. Rotations and boosts together form what are called Lorentz transformations. Galileo already understood the core principles centuries earlier. The laws of physics must not depend on the position, orientation, or constant speed of the observer. The difference between Galileo and Einstein lies in the details. In relativity, changing speed is not just motion, it is a kind of rotation. A boost is a rotation in space-time itself. In the late 19th century, physicists believed light traveled through an invisible medium called the ether, just as sound needs air. If that were true, motion through the ether should affect the speed of light. In 1887, Albert Michelson and Edward Morley performed a decisive experiment. Using Earth's motion around the Sun, which changes by about 60 kilometers per second between seasons, they built an interferometer sensitive enough to detect tiny differences in light speed. The result shocked the world. The speed of light was always the same in every direction, regardless of Earth's motion. Imagine a friend flashing a flashlight at you in space. You measure the light speed, 300,000 kilometers per second. Then you accelerate toward the source at 200,000 kilometers per second and measure again. You still get 300,000. Common sense screams that it should be 500,000, but reality refuses. From this strange fact arise the two pillars of special relativity. No experiment can distinguish between observers moving at constant speeds, and the speed of light is the same for all of them. The trick is that it is not light that adapts to us. We adapt to light. Distances shrink for fast-moving rulers. Time slows for fast-moving clocks. These effects precisely cancel any attempt to outrun a photon. No matter how hard you accelerate, light always pulls away at the same relative speed. The universe has a speed limit, and light happens to travel at it. Now return to the spaceship. But imagine you have a fleet of automated probes, each equipped with engines and atomic clocks. You synchronize all the clocks and send the probes along different routes through space, then wait for them to return. When they come back, you examine their clocks. They do not agree. Every probe has experienced less time than the clock that stayed with you. This is not a technical error. Different amounts of time have genuinely passed. Time is not an absolute value that is the same throughout the universe. Time depends on the specific trajectory of the clock's movement. Just as an odometer measures the distance traveled in space, a clock measures the distance traveled in time. If a clock is analogous to an odometer, then time is analogous to space. The special theory of relativity states that it is impossible to speak separately about distance in space and duration in time. It is correct to speak about the interval in space, time between two events. The question arises, what determines whether you are moving mainly in time or mainly in space? The answer, the speed of light. When you move slower than light, you travel mainly through time. And if you could exceed the speed of light, you would move mainly through space. But there is a peculiarity. In ordinary space, the shortest path between 2 points is a straight line. But in space-time, it's the opposite. A straight path without acceleration gives the maximum time between two events. The more you rush back and forth, the less time passes on your clock. If you could move at the speed of light, time would stop for you altogether. Movement reduces time, it does not increase it. In everyday life, we don't notice this because we crawl slower than a snail compared to the speed of light. We are like a train that always runs strictly on the rails and never deviates to the sides. There is a technique that helps to understand space-time in the theory of relativity. It is called map. Depict space and time. Show where you can move. Let's start with Newton. For him, space and time are absolute. You can specifically define moments in time. 4 dimensions are cut into 3-dimensional slices of space at specific moments. There is no disagreement about what space is and what time is. Every object, a person, an atom, a spaceship has its own world line, a path through space-time. Even sitting still, you are traveling through time because you are aging, and these world lines obey a strict rule. Once you have passed through a moment in time, you cannot turn around and pass through it again. Your speed can be anything, even 1 billion light years per second, but you can only move forward in time. In the theory of relativity, everything is different. The rule, you must move forward in time, is replaced by a new one. You must move slower than light. Unless you are a photon, of course. Then your speed is always exactly equal to the speed of light. Newton's structure of moments is replaced by a new structure, light cones. Conceptually, it's simple. Take any event, a random point in spacetime. Imagine all the paths by which light could reach or leave this event. These paths form a light cone. The rays emanating from the event are the light cone of the future. The rays coming to the event are the light cone of the past. The rule is as follows. Your world line must not go beyond the light cones. In Newton's world, the universe can be clearly divided into moments of constant time. Everything is clear, past, present, future. In the theory of relativity, this is impossible. The light cone divides space-time into 4 parts: the past of the event, the future of the event, the cone itself, and the outside of time region. It contains everything that cannot be attributed to either the past or the future of this event. In the theory of relativity, there is no concept of simultaneous distant events. What happens simultaneously for one observer may be separated in time for another. The world lines of objects must remain within light cones. These are timelike paths. If something moved faster than light, its path would become space-like, but this is impossible. The meaning of space-time in the general theory of relativity lies in the fact that there is no fundamental division between time and space. The light cones that establish the boundaries of the possible past and future for each event do not appear in addition to Newton's division of space-time into time and space. They completely replace this structure. Time can be measured along each individual world line, but it is unacceptable to consider it an inherent property of all space-time. Sean Carroll. Now rewind to 1905. That year, Einstein published a modest paper just 30 pages laying out the special theory of relativity. Soon after, he added a short follow-up note, barely 2 pages long, almost an afterthought. And hidden inside it was a conclusion so profound that it would permanently alter our understanding of reality. The energy of a body at rest is proportional to its mass. This is how the most famous equation in history was born. E equals mc squared. It's quoted everywhere, printed on mugs, referenced in movies, often misunderstood. So let's take it apart carefully. The symbol c is the speed of light. When physicists see c in an equation, they immediately recognize relativity. Squared, it becomes an enormous number. M is the mass of an object, not relativistic mass, not something that changes with speed, but the ordinary rest mass. And E is energy. Specifically, the energy an object has simply by existing, even when it's completely at rest. That's the statement. A resting object contains energy, immense energy, proportional to its mass, multiplied by the square of the cosmic speed limit. But pay attention to a deceptively simple word in that sentence: object. Not everything in the universe is an object. Dark energy, for example, the mysterious agent driving cosmic expansion, doesn't appear to be made of particles at all. Einstein's equation doesn't apply to it. And some objects, like photons, can never be at rest. They always move at the speed of light. For them, the equation also doesn't apply in its usual form. Still, within its domain, E equals mc squared is absolute. Most people associate it with nuclear weapons. That's understandable. A tiny amount of mass releasing an unimaginable amount of energy is dramatic, but that's not the point. This equation is not about bombs. It's about the structure of reality. Mass is a form of energy. Energy is constantly changing its form. Burn a piece of paper, and the ashes plus the smoke weigh slightly less than the original paper and oxygen combined. The missing mass didn't vanish. It escaped as energy carried away by photons. Every chemical reaction, every nuclear process, every star shining in the sky is quietly obeying this equation. Einstein didn't just discover a new formula. He revealed a deep unity. Matter and energy are not separate substances. They are two expressions of the same underlying thing, two sides of the same coin. And he captured that unity in 3 symbols. Special relativity was born from a deep conflict between 2 pillars of 19th century physics. On one side stood Newtonian mechanics, the foundation of all classical science. On the other stood Maxwell's theory of electromagnetism, which explained light, electricity, and magnetism with stunning precision. Both theories worked. Both were experimentally confirmed. And yet, they contradicted each other. Newton insisted that relative velocities simply add up, move toward a moving object, and the relative speed is the sum of both motions. Maxwell, however, predicted something radically different. The speed of light is the same for all observers, regardless of how fast they move. Einstein found a way to reconcile these views, but the reconciliation came at a cost. Newton's theory of gravity, the greatest triumph of classical physics, no longer fit into the new framework. Gravity is just as fundamental as electromagnetism. Einstein set out to describe it in the language of relativity. At first, it seemed like a minor task: adjust a few equations, add some corrections. But every simple attempt failed. Then Einstein returned to a familiar tool, the thought experiment, and modified it. Imagine the same sealed spaceship, but now placed near a gravitational field. Picture it in low Earth orbit. What happens to the experiments inside? How does gravity reveal itself? Einstein's answer was shocking. It doesn't. You can measure reaction rates, drop objects, watch scales, and everything behaves exactly as it would in deep interstellar space. If you wait long enough, tiny differences appear. A fork slightly closer to Earth will slowly drift away from a spoon because gravity acts more strongly on it. But this effect is subtle. Compare this to electricity. Give the fork a positive charge and the spoon a negative one. The electric field instantly pushes them apart. Easy to detect. Gravity is different. There is no negative gravitational charge. Gravity is universal. Everything responds to it in exactly the same way. Because of this, gravity cannot be detected locally by comparing how different objects behave. Einstein elevated this observation to a principle. No local experiment can detect a gravitational field. This is the equivalence principle. But I feel gravity when I sit on the couch, you might say. How do you know it's gravity? If you were inside an accelerating spaceship, the sensation would be identical. Free fall in orbit is indistinguishable from free fall in deep space. What you feel sitting on the couch is not Earth pulling you down. It's the couch pushing you up, preventing you from falling freely. Free fall is the natural state of motion. The Earth's surface constantly pushes you away from it. Many scientists would have stopped here. Einstein didn't. He realized something radical. If gravity cannot be detected locally, then it is not a force at all. It makes far more sense to think of gravity as a property of space-time itself. Gravity is the curvature of space-time. Imagine a flat sheet of paper. It obeys Euclidean geometry. Parallel lines never meet. Now imagine the surface of a sphere. The straightest possible lines are great circles, and lines that begin parallel eventually intersect. Einstein proposed that four-dimensional spacetime behaves the same way. It can curve, and that curvature can vary from place to place. When a planet appears to be pulled off a straight path by gravity, it is actually moving along the straightest possible trajectory in a curved spacetime. Now, take a clock on a satellite in orbit and a clock on a tower at the same height. Synchronize them as the satellite flies past. What happens after one full orbit? The satellite clock is in free fall. It follows the straightest path through spacetime. The clock on the tower accelerates because the ground prevents it from falling. The result is unambiguous. The satellite clock shows more time. This is not theoretical speculation. It is the operational reality of GPS. Your phone determines its position by comparing timing signals from satellites. Without relativistic corrections, GPS would drift by kilometers every day. For a satellite in orbit, one day is about 38 microseconds longer than on Earth. Engineers solve this by adjusting satellite clocks to run slightly slower, ensuring global synchronization. The central equation of general relativity is not E equals mc squared. Einstein's real equation links geometry to physics. On one side is the curvature of spacetime. On the other is everything that causes that curvature: energy, momentum, pressure. For Newton, gravity is sourced by mass alone. For Einstein, energy in all its forms matters. Even empty space matters. Vacuum energy possesses not only energy, but also tension, negative pressure. Like a stretched rubber band, it pulls space-time apart. This strange combination is what drives the accelerated expansion of the universe. And here we encounter one of the most unsettling consequences of general relativity. As Sean Carroll writes, the interaction of energy with the curvature of spacetime produces a surprising consequence. Energy is not conserved in general relativity. Not every expert agrees with this statement, not because it contradicts the predictions of the theory, but because people have widely differing opinions on how to define energy and conservation. In Newtonian absolute spacetime, there is a well-defined notion of the energy of individual objects, which we can sum to get the total energy of the universe, and this quantity never changes. However, in general relativity, which views spacetime as dynamic, energy can be pumped into or sucked out of matter as spacetime moves. For example, as the universe expands, the energy density of the vacuum remains absolutely constant. This means that the energy per cubic centimeter is constant, but the number of cubic centimeters increases, hence the energy increases. It would seem that escaping the conclusion that energy is not conserved is quite simple. We simply need to take into account the energy of the gravitational field. However, things are not so simple. It turns out that there is no unambiguous local definition of energy in a gravitational field, and this is not surprising, since the gravitational field is not locally detectable. We must grit our teeth and admit that in general relativity, energy is indeed not conserved, except in certain special cases. And yet, this does not plunge physics into chaos. However, we should not think that by admitting this, we resign ourselves to plunging the world into the darkness of chaos. Knowing the curvature of space-time, we can accurately predict the transformation of any energy source of interest. The most impressive prediction of general relativity is the existence of black holes. They are often described in a deceptively simple way, objects with gravity so strong that even light cannot escape. But, as usual, the real story is far more subtle and far more disturbing. As early as the 18th century, scientists were already imagining bodies with enormous gravity. They thought, in Newtonian terms, objects whose escape velocity exceeds the speed of light. But here's the catch. Escape velocity is not the same thing as no escape at all. To throw a baseball into space, you need to launch it faster than Earth's escape velocity. But you could do it another way. Place the ball inside a rocket and accelerate slowly. In that case, you never need to reach escape velocity in a single burst. Newtonian intuition allows escape through patience. A real black hole is fundamentally different. It is not about strength of gravity. It is about the structure of space-time itself. A black hole is a true point of no return. No amount of clever engineering can save you once you cross the boundary. The reason lies in space-time curvature. Gravity tilts light cones. Near a black hole, they tilt so severely that all future directed paths point inward. Inside, the only way out would require moving faster than light, which is forbidden. The boundary where this happens is called the event horizon. It is not a physical wall, not a force field, not an energy barrier. It is simply the place where the option return to the outside universe disappears from reality. Beyond it, only one future remains, falling toward the singularity. And here is the most counterintuitive part. The singularity is not the center of a black hole. It is not a place in space. It is a moment in the future. Once you cross the horizon, you cannot avoid the singularity for the same reason you cannot avoid tomorrow. It lies ahead in time. Crossing the horizon itself feels uneventful. Nothing dramatic happens at that exact moment. But if the black hole has the mass of the sun, you have roughly a millionth of a second left to live. Firing your engines will not save you. It will only accelerate your end. Meanwhile, your friend watching from far away will never see you cross the horizon. Your signals arrive more and more slowly, more and more redshifted. Your last visible moment freezes in time, fading away but never quite disappearing. General relativity is time-symmetric, and that leads to a strange mirror image of black holes. White holes. If black holes exist, the equations also allow their time reversed counterparts. In a white hole, the singularity lies in the past. Light cones emerge outward. Matter comes out, not in. The event horizon is ahead of you, not behind. Once you pass it, you cannot return to the white hole. So, the question becomes unavoidable. If the equations allow white holes, why don't we see them? Sean Carroll addresses this directly. Let's start with the fact that it is impossible to create a white hole. Since we are in the external world, the singularity and event horizon of a white hole are necessarily a thing of the past. So we shouldn't even worry about how to construct a white hole. If we ever discover such an object, it will mean that it has existed in the universe from the very beginning. And then he pushes the point further. If we take the question seriously, the word create should raise alarm bells. Why, in a world governed by reversible laws of physics, do we think in terms of creating things that continue to exist in the future, but not things that can travel into the past and take their rightful place there? For the same reason, we believe in free will. The low entropy condition in the past places strict limits on what could have happened before, while the absence of such boundary conditions in the future leaves a virtually infinite number of possibilities for further developments. Therefore, the answer to the question, why does the process of black hole formation seem so clear, while white holes, if we find them in the universe, are already in a mature state? It should be obvious, because the entropy of a black hole is greater than the entropy of the things it could be made of. Actually calculating entropy is quite tricky. Hawking radiation must be taken into account. The key point for us is that the entropy of a black hole is extremely high. Black holes are the ones that can shed light on the relationship between gravity and entropy, the two crucial ingredients in the ultimate explanation of time's arrow. Everyone thinks they know what a time machine looks like. A sleigh with a red chair and flashing lights, a modified sports car, a blue police box. The key detail is always the same. The machine must dematerialize in a cloud of special effects. Reality, unfortunately, is far less theatrical and far more unsettling. Time travel is possible, just not in the way fiction taught us to expect. A real time machine would look like ordinary transportation, a spaceship, an elevator, even your chair. No glowing portals, no spinning wheels. The only thing that matters is the curvature of space-time. If space-time is shaped the right way, it will carry you to the correct moment all by itself. Traveling to the future is trivial. You're doing it right now. Sit on the couch, and every hour you move exactly 1 hour forward in time. Boring? Want to skip ahead to the 25th century? Special relativity offers a loophole. Motion without acceleration maximizes the time between two events. If you want to reach the future faster than everyone else, you don't need magic. You need speed. Accelerate close to the speed of light. Fly in a loop, then return. When you come back, less time will have passed on your watch than on the clocks you left behind on Earth. The future has arrived without you ever leaving the present. The real trouble begins when we ask about traveling to the past. In a Newtonian universe, this is simply impossible. World lines can't turn around in time. Cause comes before effect. End of story. Special relativity doesn't help much either. Light cones strictly limit which events can influence which. The past remains locked away. Unless hypothetically faster than light particles exist, tachyons. If tachyons were real, strange things would happen. A tachyon could leave an event on your world line and arrive at an earlier point on that same line. You could send messages to yourself in Morse code. Don't order the shrimp, and absolutely do not go on a date with that person. Unfortunately or fortunately, tachyons almost certainly don't exist. They generate catastrophic paradoxes and are incompatible with special relativity. General relativity, however, changes the game. Space-time is no longer rigid. It bends. It twists. Light cones can tilt. We've already seen what happens near a black hole, where light cones lean inexorably inward. But nothing in Einstein's equations says they can't tilt in more exotic ways. What if they curve around and close on themselves? Imagine this. You are always moving forward in time, always staying inside your light cone. But space-time is curved so cleverly that forward eventually brings you back to where you started in the past. Your world line bends into a loop. It intersects itself. This trajectory has a name, a closed, timelike curve. This is the time machine of general relativity. To travel along it, you don't need a special device. No engine, no flux capacitor. A spaceship will do. A chair will do. If space-time itself contains such a curve, the geometry alone will carry you into the past. As Sean Carroll puts it, this is the central property of general relativity. Space-time is not set in marble. It can change, even appear or disappear, in response to the influence of matter and energy. In general relativity, it is easy to find spacetimes, and even more than one, in which closed time-like curves occur. In 1949, mathematician Kurt Gödel discovered something extraordinary. He found an exact solution to Einstein's equations describing a rotating universe, and in that universe, closed time-like curves pass through every event. Time loops everywhere. Gödel was not a fringe thinker. He was a close friend of Einstein, and the idea grew directly out of their conversations. A few years later, in 1963, mathematician and astrophysicist Roy Kerr described a rotating black hole. Inside it, the singularity is not a point, but a rapidly spinning ring. And around that ring, general relativity predicts the existence of closed, time-like curves. Then, in 1974, physicist and cosmologist Frank Tipler showed that an infinitely long, rapidly rotating cylinder of matter would also generate closed, time-like curves around itself. All that's required is sufficient density and angular momentum. But there is an even simpler construction. You don't need black holes. You don't need exotic matter. You can take ordinary flat spacetime and simply make time cyclic. Imagine something like Groundhog Day, but without any escape. Every day repeats exactly, including your actions. There is no learning, no breaking the loop, no memory advantage. The repetition is perfect and eternal. So, why do most people dismiss time travel as nonsense or science fiction? There are two reasons. The first is practical. We have no idea how to create a closed time-like curve in the real universe. The second is deeper and more troubling. It's hard to imagine what time travel would even mean. Traveling to the past seems to generate absurd paradoxes. Consider a simple setup. Imagine a time gate. Walk through it from the front and you emerge behind it one day earlier. Walk through it from the back, and you emerge one day in the future. No flashes, no disappearance. Your world line moves smoothly forward, second by second. You can walk back and forth. You can even stand, with one foot on each side. The only difference is that clocks on opposite sides disagree by exactly one day. In such a spacetime, you can easily construct a closed time-like curve. Walk backward through the gate into the past, go around it, wait one day, and meet your past self. This is where the famous paradoxes enter. The classic one is brutal. Go back in time, kill your grandfather before he meets your grandmother, and prevent your own birth. If you were never born, how did you travel back in time in the first place? There is a rule that resolves all such paradoxes. There are no paradoxes, period. Scientists don't yet know enough to say whether the laws of physics allow the existence of macroscopic closed time-like curves. If not, then there's no need to worry about paradoxes. But a more interesting question is, do closed time-like curves always give rise to paradoxes? If so, then their existence is impossible and the question is closed. However, it is quite possible that paradoxes are not necessarily the hallmark of closed time-like curves. We all agree that events that contradict logic cannot happen. In particular, in classical physics, there is only one correct answer to the question, what happened in the vicinity of a given spacetime event? In every region of spacetime, something happens. You pass through a gate, you are alone, you meet someone else, whatever. And that something is exactly what it is, was exactly what it was, and will be exactly what it will be, now and forever. If, in some space-time event, your grandfather flirted with your grandmother, then that is exactly what happened in that event. There is nothing you can do to change it, because it has already happened. Clearly, consistent histories are possible, even in spacetimes with closed time-like curves. Imagine that we have been appointed gatekeepers, and our job is to keep a watchful eye on those passing through the gate. One day, standing on either side of the gate, we notice a stranger emerge from the back of the gate. Nothing strange. This simply means that the stranger will enter the gate from the front tomorrow. Continuing to guard the gate vigilantly, we see this stranger wander around for a day, and then, exactly 24 hours later, calmly pass through the gate from the front. No one else has appeared from anywhere, and the strangers, one entering the gate and the other exiting it, form a closed loop. Those 24 hours are the stranger's entire lifetime. The story may seem eerie and improbable, but it lacks paradoxes and logical contradictions. But what if we try to rebel? Carroll addresses that too. The question that interests us most is, what happens if we try to muddy the waters? What if we decide we don't want to follow the prescribed plan? We know the answer. Paradoxes are impossible. If you have met your older self, then we can say with absolute metaphysical certainty that once you reach that age, you are bound to meet your younger self. Imagine that we removed unruly human beings from the problem and considered simple inanimate objects, such as a sequence of billiard balls rolling through a goal. There are many sets of consistent events that could occur in various space-time events, but only one of them will actually happen. Consistent histories happen. Inconsistent ones don't. At the heart of the time travel problem, physics is not the main source of discomfort. The real thing that troubles us is free will. We live with the quiet confidence that no hidden destiny will force us to act against our own intentions. Sometimes physics constrains us. Throw a person out of a skyscraper and he will fall, no matter how desperately he wants to fly. We accept this kind of predestination. But the predestination implied by closed time-like curves is something else entirely. In a universe with closed time-like curves, consistency seems to crush freedom. The atoms of your body conspire with the rest of the world, obeying mechanical laws that force you into a rigid script. But the problem runs deeper than psychology. Closed time-like curves destroy the very idea of a consistent arrow of time. Normally, we remember the past, but not the future. In relativistic language, we have access to events in our past light cone, but not those in the future one. On a closed timelike curve, however, some events lie in both cones. The past and future overlap. So what should memory do in such a universe? Remember or forget? We might be able to reconcile events on a closed timelike curve with the laws of physics at the microscopic level, but they cannot be compatible with the continuous increase of entropy along the curve. To fully appreciate the significance of this statement, consider a hypothetical stranger who walks out of a gate and then, 24 hours later, re-enters from the other side. His entire life story is thus a one-day cycle, repeating itself over and over, ad infinitum. Consider the exquisite precision required to reproduce this cycle day after day. At exactly the same time each day, the stranger must ensure that every atom in his body is precisely positioned to allow a seamless merger with his former self. He must check, for example, that there is not a single new speck of dust on his clothes that was not there the day before, that the contents of his digestive system are exactly the same as they were the day before, and that his hair and nails are exactly the same length. This is, to put it mildly, incompatible with our understanding of how entropy increases. If closed timelike curves existed, then consistent evolution in their presence would seem as strange and unnatural to us as a movie running in reverse, or any other example of events unfolding according to the entropy decreasing scenario. It's not impossible, just extremely unlikely. So, either closed timelike curves don't exist, or large macroscopic objects can't move through space-time along truly closed paths, or, well, everything we think we know about thermodynamics is wrong. Closed timelike curves create a peculiar tension. On one hand, everything appears rigidly predetermined. The system must return to exactly the same state over and over again. On the other hand, nothing is predictable. In ordinary physics, the laws work like a computer program. Specify the current state, calculate the next one, and repeat. Closed timelike curves break this logic. A stranger emerging from a gate out of nowhere cannot be predicted from any earlier state of the universe. As soon as closed curves are allowed, objects appear without origin. The very notion of a moment in time collapses. You can no longer slice the universe into clean three-dimensional instants. Determinism itself loses meaning. Perhaps the laws of physics are not instructions for evolving a state forward in time. Perhaps they are constraints on the entire history of the universe at once. If closed timelike curves were real, the philosophical debate would end decisively in favor of the block universe. Most likely, though, closed timelike curves simply do not exist, not because of grandfather paradoxes, but because space-time cannot be curved that much. Physicists have tried to build time machines, at least on paper. Astrophysicist Richard Gott tackled this question head-on. Gott is a professor of astrophysics at Princeton, widely cited in cosmology and general relativity. He had been thinking about time machines since childhood, more precisely, about why they are so hard to build. Physicists know several solutions of Einstein's equations where time travel occurs. Gödel's universe, rotating black holes, infinite rotating cylinders. But there is a catch. In all of these solutions, the time machine exists from the very beginning. We don't create it, it's already there. The real question is whether a civilization could build one. Rotation seems like the obvious tool. Tilt the light cones, bend space-time, close them into a loop. Perhaps take two massive objects, say black holes, and fire them past each other at enormous speed. Their gravity would distort space-time. The light cones would tilt. Time machine achieved. Too simple. Einstein's equations are ferociously difficult. Even modern computers struggle to model two black holes colliding at relativistic speeds. But Gott found a workaround. Simplify the universe. Instead of 4 dimensions, consider 3. 2 of space and 1 of time. This is Flatland, named after Edwin Abbott's novel. In 1991, Gott did the calculations and found that in Flatland, 2 massive objects passing each other at sufficiently high speed do indeed create closed time-like curves. The time machine works, but it doesn't count. In Gott's solution, everything is predetermined. The massive objects were always on those trajectories. The time machine was never built, it simply existed. What if we try to build one dynamically? Take 2 objects initially at rest in Flatland, attach rocket engines, and accelerate them until the light cones close. Problem solved? No. Flatland has a fatal restriction. An open universe has a maximum total energy. Add too much, and space-time closes in on itself. Gravity in Flatland does not weaken with distance. It grows stronger. No rocket, no matter how powerful, can supply enough energy to construct Gott's time machine. What about a closed universe? If an open one collapses under excess energy, perhaps a closed universe already contains just the right amount. Nobel laureate Gerard Hooft examined this idea and found that such a universe would rapidly contract. It would collapse to zero size before any closed time-like curves could form. The conclusion is unavoidable. You cannot build a time machine, not even in Flatland. General relativity allows closed time-like curves on paper. But when you try to make them real, nature resists violently. It is as if space-time itself enforces a final rule. The past is not a place you are allowed to visit. The idea of time travel fascinates us, in part because it opens the door to paradoxes and challenges our understanding of free will. At the same time, it is likely that time travel is impossible, and the problems associated with it are largely imaginary, unless you are a Hollywood screenwriter, in which case they might become your bread and butter. The arrow of time, on the other hand, is an integral part of reality, and the questions its existence raises demand answers. These two phenomena are related. A self-consistent arrow of time in the universe can exist only because there are no closed time-like curves, and many arguments against such curves arise from their incompatibility with the arrow of time. The absence of time machines is a necessary condition, but by no means a sufficient explanation for the self-consistency of the arrow of time. It seems Stephen Hawking was right. The universe jealously guards its chronology. The chronology protection hypothesis does not rest, hesitate, or negotiate. Wormholes collapse faster than anything can pass through them. Warp drives demand exotic matter that refuses to exist. Entropy relentlessly burns every bridge behind us. Again and again, every serious calculation points to the same conclusion. Nature itself destroys macroscopic time machines. If time travel were possible, actions would lose their weight. Every decision would become provisional. Life would turn into an endlessly editable draft. What would responsibility mean if every mistake could be undone? What would meaning mean if every moment could be replayed? What we call the arrow of time often feels like a prison, but physics suggests the opposite. It is the foundation of meaning itself. The past appears to be set in stone, immovable, untouchable. But that very rigidity gives the future something extraordinary: openness. We cannot return to the dinosaurs. We cannot undo that conversation with our grandfather. But in a very real sense, we already possess the most reliable time machine imaginable. Right now, you, me, all of us are time travelers. We are moving through the fourth dimension at exactly 60 minutes per hour. Our vehicle is planet Earth. Our fuel is increasing entropy. And our trajectory points in only one direction, toward events that do not yet exist. Yes, nature has almost certainly closed the door labeled was, but it has left wide open the door labeled will be. That means the only time we ever truly control is now. So don't waste it dreaming about how to change the past. Use it to create a future you would actually want to arrive in. Because whether we like it or not, that's exactly where we're going. Thanks for watching, and have a safe trip.